Hello everyone. In this lesson, I will start section 3 integration methods. In this section, we will be studying two different kinds of integration techniques. In derivative, we had a product rule for the functions that are multiplied and quotient rule for the functions that are divided. To take their derivative, we applied quotient and product rules. But in integration, we don't have such simple rules to integrate multiple functions multiplied or functions divided. We will be using two different techniques to be able to multiply or divide functions inside the same integral notation. The first technique we're going to study is integration by part, but this technique it takes time and it's a little bit confusing for students, so I don't suggest you to use that way. There is an equivalent way which is called integration by table. So by this method, we can solve questions that we can solve by integration by part. So this way is easier, simpler, and time saver. So let's start and talk about what integration by table mean and how it works and what kind of situations we can use that table. So this technique is used when there are product of two different kind of functions, like algebraic function and an exponential function are multiplied. Let's say an algebraic function and trigonometric function is multiplied. Algebraic function and logarithmic function is multiplied. Logarithmic by trigonometric, exponential by trigonometric. So we have two different kind of functions are multiplied under the same integration symbol. Then we can apply integration by part or integration by table technique. So I'm just going to explain how integration by table works. So this technique allows us to view something and see as product of two things, one of which can be easily integrated, other can be differentiated easily. So we have two functions multiplied by each other. We're gonna pick the one that can be easily differentiated. The other one can be easily integrated. So let's take a look at our first example. Exercise 3 in the book. We are given integral x squared times e to the x dx. So when I differentiate x squared, it is easier to differentiate this because as I differentiate x squared, it reduces complexity, right? It makes the function easier every time when I differentiate it. When I take derivative of x squared, it's going to be 2x. If I take derivative of 2x, it's going to be 2. Take derivative of 2 one more time, it's going to be 0. So as I differentiate this function, I got 0. So this function is a function that can be differentiated easily because every time when I take derivative, it reduces complexity, it simplifies the function down. So I am going to differentiate this algebraic function here, and I am going to integrate this exponential function and the other one. The integral of e to the x is e to the x. Now, after this point, I'm going to multiply these two across. Those two. Multiply this by this and put plus in front. Multiply those two, put minus in front. Multiply these two, put plus in front, and you stop because there is nothing left on the right to match with 0. So the signs are going like this, plus minus, plus minus, plus minus, like that. And I multiply each couple and add them up. So integral x squared e to the x dx is equal to, multiply each couple and add them up, x squared e to the x. Here there's minus in front, 2x e to the x, and there is plus in front of this, plus 2 e to the x. That's it. In one step, I integrated my function. If I try integration by parts, this will take 2 times more than this. We are going to be needing using the same method twice if we were using the integration by part technique. So integration by table technique is easy, simple. We just differentiate one of the functions, integrate the other one, you multiply them across and add them up. This is the result. Okay. Okay, let's move on to the next question, exercise 1. X sin x. We have an algebraic function, a polynomial function, and a trigonometric function. Two different kind of functions are multiplied. So, as in the previous question, the polynomial function is easier to differentiate. Derivative of x is 1, derivative of 1 is 0. The other one will be integrated. Integral of sine is negative cosine, integral of cosine is sine. So, in between, you multiply them across. X with negative cosine x, 1 with negative sine x, put plus in front of the first pair, minus in front of the second pair. Now, the result will be written as x times negative cosine x, so negative x cosine x, negative negative makes positive, 1 times sine x. So this is my answer. Oh, I forgot adding c. Previous question also I had c. Okay, that's it. So here are similar exercise questions that you can find in the book. Okay, another type of question. Instead of asking the result integration, it is asking about a specific antiderivative. Exercise 15. Find antiderivative of f that passes through the given point. Like we did in the first section, we are asked to find antiderivative for a specific point, then we integrate the function and substitute the given point in the result. Let's try. We have x and cosine x over 2. X, the algebraic one, can be easily differentiated. Derivative of x is 1, derivative of 1 is 0, like that. Integral of cosine x over 2 is sine x over 2 divided by 1 over 2. So in denominator, having 1 over 2 will bring 2 in front. Now, integral of 2 sine x over 2. Integral of sine is negative cosine. I had 2 in front. I will have divided by 1 over 2. Flip it. 2 makes 4. Okay, so I am done. When I see 0, I stop. Now match them, pair them. This by this by this. Plus for the first pair, minus for the second pair. Now write the result. Integral of x by cosine x over 2 is equal to x by 2 sine x over 2 and minus minus makes plus 4 cosine x over 2. And I additionally have c. So this is how we integrate this function. Now I'm supposed to find antiderivative at this point. So try this point. If this is capital letter f of x, then my x is 0. X is 0 when my result is 3. So what is my c? Okay, 0 times sine, this is 0. Cosine 0 over 2 cosine 0 is 1. Here I have 4 on the left. 4 plus c on the left equals 3. Then c is equal to minus 1. So I got my c. I can write this antiderivative, which is equal to 2x sine x over 2 plus cosine x over 2 plus c, which is minus 1. So I got my specific antiderivative. All right. Okay, another type of uh, multiplication questions. I have integral ln x. There's nothing multiplied by ln x. We can consider there's an invisible one here. This is an exercise question and it came in Wazari twice, the same question. So when I pick the function that can be easily integrated, I cannot integrate ln x because the question is itself integrating ln x. I don't know how to integrate. That's why I'm applying this way. So I have to use ln x for the one that can be differentiated easily. Derivative of ln x is 1 over x. Derivative of 1 over x is negative 1 over x squared. Derivative of negative 1 over x squared is 1 over x cubed and stuff 2 over x cubed and stuff. It keeps going as increasing its complexity. So when I keep taking derivative of this function, instead of reducing the complexity, I will increase the complexity. So I won't keep differentiating this function. I will just take derivative once and stop. Because unlike the previous questions, we will never go to zero. The answer will, the derivative will never be zero. So I will just stop when I take derivative once. The other one will be used for differentiation, which is an invisible one. Integral of 1 is x, and I stop. How am I gonna match this? I'm gonna multiply these two together, put plus in front, and those two together horizontally, put minus in front. But in front of this product will be put in integral. This is different than the other type of questions. This will be put under integral symbol. So integral of ln x dx is equal to ln x times x minus, inside integral symbol, we're going to multiply these two. 1 over x over times x is 1. Integral of 1 is x, right? So my answer is x ln x minus x plus c. So it seems complicated, but when you get the idea, you'll solve the questions easily. So for ln questions, this is how it works. We use ln for differentiation, for the other function that's multiplied for integration. If there's nothing multiplied, we're gonna use this as 1. Integrate 1 once, differentiate ln x once, and multiply ln x and x, subtract off the product of these two inside the integral, and take integral of this. So here we can use a hack way to identify which function to differentiate easily. Late. What does that mean? If there is ln function in the question, you can use this ln function to differentiate. If there is no ln, algebraic function, like cubic functions, like quadratic, like polynomial functions, we use this algebraic function to differentiate. If there is no algebraic, trigonometric, you use trigonometric as differentiation, and if nothing, we use exponential. So this is the order of choosing functions if we have multiplication of two of them. Okay, so generally we have algebraic function in the questions, so we use the algebraic one to be differentiated. If no algebraic, we use ln function to differentiate. If there is algebraic and ln together, we use ln to differentiate. If there is ln, ln will be differentiated. If there is no ln, algebraic will be differentiated. So you can use this hack way to determine which function should be differentiated, or you can just try. Okay, for this ln type questions, we can come up with a formula. Instead of doing this, dealing with this stuff, if ln is alone, no function is multiplied by ln under this integral symbol, then we can say the formula of finding integral of ln is x ln minus x plus c. X ln minus x plus c. No matter what your angle is, it's always x multiplied by this original uh, function minus x plus c. Okay, one last question. In this topic, we also have some questions involve definite integral, like this. Ministry exam question: find the result of integral from 1 to 2 of ln 2x. So ln is alone, nothing is multiplied by ln. We can do it in a long way, or we can just use the formula. The formula of finding integral of ln 2x dx is x ln whatever x minus x plus c. So this is how we take the integral, either memorizing this formula or using this integration by table technique. Okay. Now I got my integral. Now I'm just going to evaluate this integral at 1 and 2. Substitute 2 first and then 1. 2 ln 2 times 2 minus 2 minus, in a bracket, 1 ln 2 times 1 minus 1. Let's try to simplify. 2 times ln 2 squared minus 2 minus ln 2 minus plus 1. Here, I am going to apply a logarithm property here. If you remember, logarithm property. If you remember, whenever there is a power inside the for the argument of the logarithm, let's say we have x to the power a, then we can bring this power down in front of the logarithm and write this as a times ln x. So I'm going to apply this power property, log power properties that you studied in grade 11. So let's bring this 2 power down in front. So it's gonna make 2 by 2 ln 2 minus 2 minus ln 2 plus 1. 2 times 2, 4 ln 2. I have minus ln 2 minus 2 plus 1. So here I have 4 ln 2 minus ln 2, which is 3 ln 2. Minus 2 plus 1 makes minus 1. No more simplification. This is the final answer, which is option D. As you can see, there are many ministry exam questions by the same idea. So that's it for the first technique, integration by table or integration by part. Next lesson will be about the second technique, integration by substitution.